In this lesson, we will be studying logarithmic functions. For short, I may just call them log functions. To get us started, let's start with an exponential function, 2 to the power x. Now, we studied exponential functions in the previous lesson. We learned that they are one-to-one functions, so their inverse exists. The inverse function exists. So let's find it. If you remember, the first step in finding the inverse function is replacing f of x with y, and then interchanging x and y, and then finally solving for y. But at this point, it's very difficult for us to solve for y here. So instead of solving for y using an algebraic technique, I will solve for y using words. So y is the exponent. Now that's very important, that y is an exponent, okay? Keep that in mind. Y is the exponent to which you raise 2 in order to get x. And the symbol we use all the time for to represent equality is the equal sign. So y equals the exponent to which you raise 2 to get x. Now don't forget that when you find the inverse function, the last step is to replace y with inverse function notation. So therefore we have f inverse of x is the exponent to which you raise 2 to get x. Now, what I'm going to do is introduce special notation that would represent these words, the exponent to which you raise 2 to get x. And that's exactly what we have here. F inverse of x is equal to log base 2 of x. This notation means the exponent to which you raise 2 to get x. Now 2 here is your subscript. X is called your argument, but 2 is the base of this logarithm. It's the base or the subscript. So this represents that base here of the exponential equation. Same base. So all of this notation is the exponent to which you raise 2 in order to get x. Now what I want us to do now is graph both of these functions on the same coordinate system. Now we did this in an earlier lesson. We were graphing functions and their inverse in or on the same coordinate system. Remember, exponential functions go through the point 0, 1 and 1 comma the base, so it goes through 1, 2. And so the curve looks something like this. This is the curve for the exponential function. Also remember that the curve gets infinitely close to the x-axis, which is your horizontal asymptote, y equal to 0. And then remember that what we can do is just switch these coordinates, the order of the coordinates, in order to get the graph of the inverse. So instead of 0, 1, we'll have 1, 0. Instead of 1 comma 2, we'll have 2 comma 1. And watch this, everybody. Instead of the x-axis being an asymptote, I'm going to have the y-axis be the asymptote. So for a logarithmic function, the y-axis is a vertical asymptote. So I'll get infinitely close to the y-axis as a vertical asymptote, but I'm not allowed to cross it. So these are the graphs of f and f inverse. This is the graph of an exponential curve. This is the graph of a logarithmic curve. Now don't forget that the graphs of a function and its inverse are always symmetric with respect to the line of symmetry. I hope you remember this from an earlier lesson that you and I were studying. This is the line of symmetry called y equal to x. Now, it's also called the identity function. These two graphs, the yellow and the green, f and f inverse, the exponential and the logarithmic, they do not intersect each other at all. Now here's the formal definition for a logarithm. For all positive numbers b, where b is not equal to 1, and all positive numbers x, let's stop right there just for a second before I continue reading. B here represents the base of your logarithm. And they just said that the base of your logarithm has to be a positive number. Why? Well, it comes from the exponential function. Remember, we talked about this in an earlier lesson. The base of an exponential function has to be positive. for reasons that we mentioned in an earlier lesson. So because the base is positive, it's the same as this base for the logarithm, so the base, therefore, by default, must be positive. Not only that, it must not equal 1, and x must be positive as well. Now here it is, y equals log base b of x is equivalent to, it means the same thing as x equals b to the power y. Okay, let me be very clear what's happening here. This left-hand side is logarithmic form. This is a logarithmic equation. And the right-hand side is an exponential equation. Any logarithmic equation can be rewritten as an exponential equation. And actually, we'll practice doing that in just a minute, rewriting a log equation as an exponential and vice versa. A little bit more terminology for us before we move forward. B is called your base, x is the argument, and y is the exponent. So they're saying that the base has to be positive and the argument also has to be positive. Now all of this represents the same thing over here. This is equivalent rather. X is the argument, b is your base, and y is your exponent. All right, so what we're going to do is we're going to take this log equation, this logarithmic equation, and rewrite it as an exponential equation. Now notice that your base is 5, your argument is 25, and this is your exponent. So what I like to tell my students to do is this little tail trick. Take your base, raise it to this power, and then you will get this number. Some students call that like a little scorpion tail or whatever. But at the end of the day, this means, in exponential form, base 5 raised to the power of 2 gives you 25. And we can tell we're correct here because this makes sense, right? 5 squared is 25. So this exponential statement is equivalent to this logarithmic statement. Check out this new log equation. Log base 2/3 of 8/27 is equal to 3. So you can do your little tail trick if you like that. You don't have to do that if you don't want to, but the base is 2/3. You're raising that base to the power of 3, and you get 8/27. And that's true, isn't it? 2 cubed is 8, and 3 cubed is 27. One more for you. Log base 2 of 1/8 is equal to -3. Just remember that the base has to be positive, and it is, and the argument has to be positive, and it is. This is the exponent. That's allowed to be any real number. So if you do your little tail trick here, you'll get 2 raised to the -3rd power, right? Gives you 1/8. So 2 raised to the -3rd power gives you 1/8, which is true. So that's how you can rewrite a log equation as an exponential equation. Now let's go the other way around. So write each exponential equation as a logarithmic equation. Now, when you write a logarithm, well, first of all, when you write a log equation, you need a log. And then the subscript is your base. And when you look at this exponential equation, the base is 3, the exponent is 1/2, so this must be the argument. The base is 3, so I'm going to write down the subscript of 3, right? That's your base. Now a logarithm is an exponent, and the exponent that you see is 1/2. Please don't lose that translation. A logarithm is an exponent. So you always want to set your log equation equal to the exponent because a logarithm is an exponent by definition. The exponent is 1/2, so that goes on the right side of the equal sign. So then the argument must be the square root of 3. If you raise 3 to the power of 1/2, you'll get the square root of 3. 1/5 raised to the -1st power is 5. This would be a great opportunity for you to pause the video and to try to rewrite this as a logarithmic equation on your own. Okay, so here's my logarithm. My base is 1/5. My argument is 5, and my exponent is -1. I hope you did pretty well there. Let me give you another one. 2 to the 0th power is equal to 1. So as a log equation, it'd be log base 2, right, of 1 gives me 0. Good job, everybody. We rewrote each equation in the opposite form. Very good. All right, so what we're going to do now is we're going to start solving some log equations. This says solve the logarithmic equation for x. The directions should say solve each logarithmic equation for x. Can I fix that really quick? I forgot the word for. All right, there, I fixed the directions. We're going to solve for x. Now, one strategy I have for you to solve a logarithmic equation I think is really helpful is to rewrite the equation as an exponential equation, and then you can solve. So as an exponential equation, this would be read as x squared, x to the power of 2, gives you 9. And that's fantastic because now you and I can use the square root property on both sides, right? And you and I will get two solutions. Either x is positive or negative 3. Now you have to be careful when you're solving log equations because it's very often where you can have an extraneous solution. Now remember what you solved for. You solved for x, and x here was your base. And in the definition for a logarithm, we said that the base must be positive. So we have to dismiss negative 3 because it's extraneous, and our one and only answer is positive 3. So be very careful when you're solving to make sure you don't get any extraneous solutions. Let's try another. We have log base 2 of x is equal to 4. This time around, it's not the base that's unknown, it's the argument that's unknown. I advise you to do the same thing. Rewrite it as an exponential equation. As an exponential equation, this is going to be read as 2 to the 4th power will give me x. That is 16 is equal to x, or x is 16. Now before you box it, remember the argument must be positive. Oh, thankfully it is. So this is our final answer. X is 16. Here's our last one that we'll look at, and it's log base 1/7 of 1/49 is equal to x. Again, I'll do the switcheroo, if you will, to an exponential equation. So you have 1/7 raised to some power of x will give me 1/49. Okay, now I want you to use inspection here, right, and intuition. If you raise 1 to some power, it'll give you 1. Well, that would have to be 1, well, anything really, right? 1 squared is 1, 1 cubed is 1, 1 to the 4th power is 1. So let's continue thinking. 7 raised to some power gives you 49. Oh, that would have to be 2. 7 squared is 49. So x must be 2. The exponent that you would have to raise 1/7 to in order to get 1/49 is 2. You'd have to square 1/7 in order to get 1/49. Now, this is not an equation, it's just an expression, and they want you to evaluate it. They want you to find the value of this expression, log base 9 of 81. Now, what I do not want you to forget, actually I want you to write it in your notes really bold and highlight it, put a box around it, is the statement that a logarithm is an exponent. So when they are asking you to evaluate a logarithm, they're basically asking you, what is the exponent? That's what it is. A logarithm is an exponent. So here they're asking you, here if you'll allow me, I'll rewrite it this way. The base is 9. They're asking you, what do I need to raise 9 to in order to get 81? And when you think of it that way, I think it's a little more clear. Oh, you would have to raise 9 to the power of 2 in order to get 81. 9 squared is 81. So 2 is the answer. 2 is the exponent to which you raise 9 to get 81. Check out this one. Log base 11 of 1/121. Now this is saying, what do I raise the base of 11 to what exponent, in order to get 1/121? Now, we know that 11 squared is 121. But in order to get 1 over 121, the reciprocal, then it must be negative 2. 11 raised to the negative second power will give you the reciprocal of 121. It'll give you 1 over 121. Now remember, the exponent can be any real number, okay? It's the base that has to be positive and the argument that has to be positive. Now this one may require some thinking here. Log base 8 of 2. That means 8 raised to some power gives me 2. Now let's do some brainstorming here. If you raised 8 to the 0th power, you would get 1. If you raise 8 to the first power, you will get 8. The question is, what do I need to raise 8 to in order to get 2? Well, if 8 raised to the power of 0 gives you 1, and 8 raised to the power of 1 gives you 8, that must mean the exponent that they want me to find must be between 0 and 1. That must mean it's a fraction. Now, remember the relationship between 8 and 2. 8 is the third power of 2. Said another way, 2 is the cube root of 8. So, what if the exponent was 1/3? Would that work? Well, let's see. 8 raised, let me write it for us. 8 raised to the 1/3 power. Does that give me 2? Well, we learned in an earlier lesson that a rational exponent like this, 1/3, means the same thing as the cube root of 8, right? Does that give me 2? Yes, it does. The cube root of 8 is 2. So I know that the exponent that they were looking for here, my answer, is 1/3. 1/3 is the evaluation. Actually, let me not scroll down here. Let me go over here. So log base 8 of 2 is equal to 1/3. 1/3 is that exponent, okay? 1/3 is the answer. Now, a common logarithm is a logarithm whose base is 10. Now, what's really important to note is that if there is no base written, then the base is assumed to be 10. All right, so let's evaluate some common logs. Here's the first one, log of 100. Now you can see that the subscript is not written. The base is missing, if you will. Whenever the base is not written, it is assumed to be 10. So this is log base 10 of 100. So really this is asking you, to what power do I raise 10 in order to get 100? What is this exponent? And so now I hope that you can see, oh, log of 100, that's equal to 2, because 10 squared is 100. So log of 100 is just equal to 2. 2 is the power to which you have to raise 10 to get 100. Now we have log of 1 over 10,000. Now remember that the base is not written, so the base must be 10. 10 raised to some power will give me 1 over 10,000. Now what I know to be true, so I'm going to do some brain work here. What I know to be true is that 10 raised to the 4th power will be 10,000 because there are 4 zeros here. If you count them, 1, 2, 3, 4, which correlates to the power of 4. But I don't want 10,000, I want 1 over 10,000. That must mean 10 raised to the negative 4th power will be 1 over 10,000. So the answer here is negative 4. This is the exponent that they wanted us to find. Next one, log of negative 100. Now, what this means is the base is 10, right? Because this is a common log. And we'd have to raise 10 to something in order and get negative 100. Now, this is impossible because your base is positive. And no matter what you raise 10 to, you'll never get negative anything. Negative 100 for sure, you will never get that because your base is positive. Also, don't forget that the argument, by definition, must be positive. Here, the argument is negative, so this is no solution. maybe I should say undefined better. This is undefined. All right, very good, everybody. We're going to wrap this lesson up by graphing some log functions. All right, the first thing, or the first one I want you to consider is log base 3 of x. I've created a little table here for our values. Now, usually, I don't know how you, what your experience has been, but for me at least, usually we choose something for x and plug it in and then find y. I want to turn it around. Okay, let's choose a y value or f of x value, and then we'll find x. Remember, this is your base, this is your argument, and this is your exponent. So let's choose an exponent first. We'll choose that exponent, we'll raise 3 to that exponent, and that'll give us x. Okay, so for example, let me do the first one for you. How about 0? If you raise 3 to the 0th power, you'll get 1. So 1 comma 0 is on our curve. Now let me just show this really quickly. This is what we did here. Sorry. F of x was 0. So we had this, right? That's what we did. We plugged 0 in for y. And then you and I did this a little while ago. 3 raised to this power gives me x, right? Remember that when we switched it to an exponential? So 3 raised to the 0th power gives me x. That is 1 is equal to x. So that's how I found that. Let's choose another power for y. How about 1? 3 raised to the first power will just give you 3, right? Let me show you what I did. What I did was I let y be 1. So I have 1 is equal to log base 3 of x. And so if you rewrite this, it'll be 3 raised to the first power gives you x. 3 raised to the first power gives you x, or x is 3. Isn't that cool, everybody? How about negative 1? So 3 raised to the negative first power would be 1/3. Right? Okay, let's go to the plane and see what we have so far. Now remember, by definition, the argument must not be negative. The argument must not be negative. That means x cannot be negative. Anything to the left of the y-axis, your x values are negative. So that's why I'm not showing anything to the left of the y-axis, because over here x values are negative. So let me plot these points for us. 1, 0, that's an x-intercept. 3, 1, and we also have 1/3 negative 1. 1/3 negative 1. It's about right there. Now, what we also know to be true is that no matter what you raise your base to, right? No matter what you raise your base to, you will never get 0. This will never happen, right? No matter what you raise 3 to, you'll never get 0, right? So this curve will get infinitely close to x equal to 0. In other words, it'll get infinitely close to the y-axis, but it will never cross it. What I'm trying to convince you of is there is a vertical asymptote right here on the y-axis. So when you draw your curve, make sure you get infinitely close to the y-axis, but that you never touch it, all right? Never cross it. So there's your logarithmic curve. Notice that this curve would be considered, or this function would be considered, an increasing function because it's going up from left to right. Your function values are increasing as you read your graph from left to right. Let's graph another one. G of x is equal to log base 1/3 of x. Notice now that your base is a fraction. Okay, so let's do this. And let's plug in some y values, some g of x values. So basically, you're going to choose some exponents to which to raise 1/3. Let's start with 0. If you raise 1/3 to the power of 0, you will get 1. Oh, notice this is the same x-intercept that we got earlier. Let's raise 1/3 to the power of 1. 1/3 raised to the power of 1 gives you 1/3 right back. Okay, let's raise 1/3 to the power of -1. If you raise 1/3 to the power of -1, here, let me show you that one. 1/3 raised to the power of -1, it'll reciprocate this and just be 3 over 1, which is just 3. So then the answer here would be 3. All right, let's plot some points, but please notice that the y-axis is going to be your vertical asymptote. It's impossible to raise the base of 1/3 to any power and get 0. So we'll get infinitely close to the y-axis again. All right, we have the same x-intercept. We have 1/3 comma 1, so that's about right there. And then we have 3, -1. So this curve behaves like this. Now this curve would be considered going down from left to right. Your function values would be. So this function would be considered decreasing. Notice your base is a value between 0 and 1. It's a fraction that's less than 1, and the function is decreasing. All right, let's make a summary of the graphs of log functions of the form f of x is equal to log base b of x. We did something like this for our exponential functions. All right, first things first, domain. Remember, the domain is a set of your x values, and for a log function, x is your argument. And in the definition, they said x has to be positive. The argument has to be positive. So that must mean the domain is a set of all of your positive values for x. So there's my domain. Now you can see in the graphs that we graphed earlier, your range is all real numbers. If you'll allow me to scroll back up here, how low is this curve going? It's going down forever eventually and going high to infinity, right? And never stops increasing. And the same is true of the first curve that you and I graphed. So therefore the range will be all real numbers. Okay? Now the asymptote will be vertical. It'll basically be the y-axis, and so the equation that defines this vertical asymptote is x equal to 0. But just remember, the x equal to 0, this is basically your y-axis, behaves as the asymptote, okay? X-intercept, notice that for both of these functions, the x-intercept was 1, 0. And then we did not have any y-intercepts because the curve was getting infinitely close to the y-axis but never touching it. Let's talk just about a couple more things. Notice that these functions are one-to-one, right? Their graphs pass the horizontal line test. So they are one-to-one. Now that is not surprising to us because we got these functions, right, or this log function, by starting with the one-to-one exponential function. That's where it came from. So we know that if an exponential function is one-to-one, its inverse function, the log function, will also be one-to-one. Now the last thing I want to say is notice that in the first function that we graphed, the base was 3. And when the base was 3, we had an increasing function. The second curve, the base was 1/3, and our function was decreasing. So very similar to exponential functions, if the base is greater than 1, it'll be an increasing function. If the base is a fraction between 0 and 1, it will be a decreasing function. All right, so here's our summary. Now I just want to draw a few observations here. Now these are very, very, very important observations. Notice that this, all real numbers, is the domain for exponential functions. This, positive values only, is the range for exponential functions. So notice that the domain and the range between exponential and logarithmic functions swap, right? And that makes a lot of sense to us because when we were first studying inverse functions, we mentioned how the domain and the range swap, right? As do the coordinates. Instead of x going to y, you have y going to x. And what used to be the domain is now called the range, and what used to be called the range is now called the domain. So although this is the domain for log functions, this is also the range for exponentials. This is the range for log functions, and it's the domain for exponentials. I want you to notice a few other things. Log functions have a vertical asymptote, while exponential functions have a horizontal asymptote. The equation for the vertical asymptote of a log function is x equal to 0. The equation for the asymptote of an exponential function is y equal to 0. Let's keep going because this is just really, really fascinating. When we were studying exponential functions, we said that they had a y-intercept of 0, 1. But now when we study log functions, it's an x-intercept of 1, 0. Please notice the switch. And then when we were studying exponential functions, we said exponential functions do not have an x-intercept. But now here in log functions, we don't have a y-intercept. So please notice the relationship between exponential functions and logarithmic functions. All right, to wrap this lesson up, what we're going to do is we're going to graph a function using transformations. Now, this is log base 2 of x plus 1. Because this plus 1 is within the argument, right? It's within the parentheses. This plus 1 represents a horizontal translation. And remember, with horizontal translations, it's the opposite of what you might think. So because it's plus 1, it represents 1 unit to the left. All right, very good. Now the next thing I would love for us to do is to identify the parent function for this log function. Now, because the base is 2, therefore my parent function is simply log base 2 of x. Okay, everybody? So basically take away the transformation. Now we know a lot about this curve because we just wrote a summary for functions that are of this form. So let's graph this curve, the parent function, and then we'll move that curve 1 unit to the left to get the function g. All right, so here we go. We are going to graph the parent function, log base 2 of x. We'll graph that first because it's our reference. As I'm doing this, I'm realizing that I forgot to write something down for our summary. Can we go back in our notes, please? So I'm going to just scroll up here, but I want you to go back to your notes, please, for the summary of log functions of this basic form. So if I can just scroll down, right there would be perfect. I forgot to mention that you always get one free point, well, I call it a free point, that is on your curve, and that is your base comma 1. So please add this to your notes. And you know what? If you want to refer back to the 2 graphs we mentioned, go ahead and do that. But I want you to remember that for exponential functions, exponentials, you had a free point 1 comma the base. But now here for log functions it's the other way around, the base comma 1. The base comma 1. So now let's go back to our problem. So sorry that I forgot about that. Here, if I'm trying to graph this function, I know that I will get the point base comma 1. That is 2 comma 1. 2 comma 1. That's the base comma 1. And we also know that we'll have an x-intercept 1 comma 0. All right, so this is my curve. This is the parent function. Now remember to get infinitely close to the y-axis because there's a vertical asymptote there. This is the parent curve. All I need to do to get the curve for function g is to move 1 unit to the left. So that's fairly simple. If I move this point 1 unit to the left, it's at the origin. If I move this point 1 unit to the left, it's at 1, 1. Like that. Now before I draw the curve, I want you to notice that the asymptote used to be here, right? The y-axis for the parent curve. But everything got moved 1 unit to the left, including the asymptote. So now the asymptote is here, not at x equal to 0, but at x equal to negative 1. So I'm going to draw that in here, so that way I don't accidentally go too far. So my curve looks like this. this. This is the curve for function g. It's the same curve, it's just that my whole curve got moved over 1 unit to the left. Can we label our asymptote, please? By the way, if you're ever looking for the asymptote, what you can do is you can always take your argument, you can set it equal to 0 and solve. Let me show you that. If I take my argument, set it equal to 0 and solve, you would get x equal to -1. That happens to be the vertical asymptote right there, x equal to -1, okay? Now before we move on, let's write the domain and the range for function g. Remember, the domain is read from left to right. How far left is this green curve going? Well, it's getting infinitely close to your asymptote, which is at -1. It'll never reach x equal to -1 though. So let's start with -1, put a parenthesis there because that's an asymptote, and then it's going to the right forever. So from -1 to positive infinity. And the range, well, that's all real numbers because it's going down forever and up eventually forever. So all real numbers there. So notice that the transformation changed your domain, but it did not change the range. All right, everybody, I hope you enjoyed studying log functions and how to graph them. You'll get more practice with the homework section, so good luck with that. And thanks for sticking around and taking really good notes. I'll catch you in the next lesson. See you later.